Well, hi guys, it's Cliff here from Down Under. So carrying on with my videos on CNC job setup and run, making these grinding wheel hubs. So this is going to be part 2. If you've stumbled on this video out of sequence, there's a part 1 that's worth watching first. So I'm making up these grinding wheel hubs. I'll run a little clip now to show you the content of these videos, see whether it's something you'd be interested in. Cheers! I'm just not sure how long I should take on this part of it because it could take up an awful lot of time. So do your various little sections of code on the conversational OD code. Have a look at my file here. So I've got OD1, OD 49.7, OD rad. You know, each time we produce a little bit of conversational, we're naming it so we can clearly identify it. Then we bring them all together by going to conversational edit, and then you can pull all the different little sub-programs together and save them hub all, and this is the OD combined through that process. Okay, so now it's a really good idea to blow up the display here and have a good look at it. Have a look. For example, there was an issue after producing this little radius on the corner here. The software didn't back it out far enough in the Z, and it backed it down to diameter here for the next little bit of code, which was this chamfer here, and it just scraped on that diameter. So I could have seen that if I had my wits about me and looked at that little dotted line going down slightly below the surface. This is the remaining metal here, and you can really get a good feel by looking at the graphics for any potential crunch ups. So have a good check there. So now we've got all of those OD turning parts combined into one. I'll run that now. That'll save a little bit of time as against going through them all individually. But the first time you produce them, I would do them all individually as one-offs, just to check it until you become more experienced, and then combine them all. And be careful when you combine them all, depending on what version of the software you've got. When you combine them all, if you've done any hand editing to the individual little bits of code, when you combine them, it goes back through the conversational software somehow. I don't really understand all this, and it can revert it back to its default settings, and so some little adjustment you made may be gone. So what I would say to do is every time you hand edit, write it on a bit of paper that you've made these hand edits. Then when you've combined them all together, check them that they're all still in there. Is a safety thing. Maybe in the more recent versions of the software, Tormach will have got around these problems. There's 3 or 4 different little things that can go wrong there if you're not careful. So write down any hand editing and check it before you run it after you've combined it. Alright, well I'm going to run that hub all, but imagine that you just produced your first little bit of OD turning, and I'm just going to advance slowly on the maximum velocity slider and get it started, and then we'll just keep running. We'll just stop there and have a look at your DROs and look at the display, look at your tool clearances. Is the drill going to hit on the chuck drawer? All those things. Final finish pass. Then we're going to start on some new tool path, the OD turn. Have a look at the chip braking so it can run automatically. There we are. So you can see there that this job will run automatically. So the key choice is what type of tool you use. This is an ISCAR, industrial quality trigon type tool. It's got 6 edges. I find it lasts really well, chips breaks really well, and so it's worth spending the money on good quality tooling if you want to run your machine automatically. Surface finish is a little bit rough because it's medium tensile steel, but for the application it's fine. I don't need to worry about a razor sharp finishing tool because it's only a grinding wheel hub. So the other key thing for running automatically is to set your feeds and speeds. This critical part here, the chip load and the speeds, depths of cut. I'm taking a 1 millimeter on the radius, 2 millimeters on the diameter depth of cut to get that chip breaking. Alright, so now you've done that, maybe you'll now open up the conversational again and produce the tool path for the thread. So make sure you name it clearly, you know, hub thread, and set all the various settings here, allowing length in the Z to clear the tool up against that face, so we're back 1 millimeter there, number of passes. So you can set your depth of cut reasonably deep because it reduces with each cut as you go down. So I'm starting with a 0.4 depth here, and it'll end up with a very slight cut. So that'll be a total number of passes of 19. So you're setting all the various settings here. Spindle RPM for that diameter about 900, and then we post that to file. Now running the thread for the first time is a little bit scary because you can slow down your maximum velocity slider to approach the work and check your display and check clearances that's fine, but once the thread starts, you can't slow it down or pause it anymore. You've just got to be sure right from the beginning that there's not going to be a crash. So we'll bring it up as close as we can, pause it, say about there, and have a good look at your display and everything else and say, okay, here we go. So that was set up with the conversational, or the 0.4 depth of cut. What's that, about 16 thou in the beginning? That was quite light. I probably could have gone to a 0.6 depth of cut in the beginning and it would have reduced down, and then instead of all of those passes it would have been a few less. But it's best to err on the side of caution, and that worked fine, so I'll just leave it at that. Oh, that's really nice. Perhaps a little bit loose, but not too bad. It's fine for this application. So the way you can set the fine-tune the thread depth is to set it a little bit shallow to start with, X end, you know, make it a few thou bigger, run it, test it, and if the nut is too tight, reduce it, redo the conversational code, save it over the top of it, and run it again. Now I've found in the past that the thread keeps its pitch, keeps its position, and it will recut over the top, at least with the versions of software and the method that I've been using. But don't quote me on that. It's possible that that might not work in the future, but it's worked for me every time so far. So if I wanted to change the fit of the thread, I just put in a set of 16.2 end, you know, 16.3 or whatever. Just check I haven't changed anything else, and then post to file, hub thread, you can see up there. Find your hub thread and save over the top. And now we've got a slightly tighter fitting thread. So you can go through and adjust your codes very easily like that. So for fine-tuning your thread size, you can redo the conversational, or you can go into your offsets table and in your wear offsets just add a little bit there. If you just put in, say, 0.1 of a millimeter, that will make it that much bigger, for example. So that's another alternative. So then we're going to spot the center with the spotting tool. We're only going to go a couple of millimeters deep. Then we're going to go down to this gang tool position for our tapping drill, 6.8 millimeter. Well, let's just have a quick look at this on the conversational. So I think it's really important, again, if you want to run the job automatically, is to have plenty of retraction. So we're going to have a peck depth of 1 millimeter or 40 thou, so it's constantly coming in and out, and we've got a good flow of coolant on the tool. Alright, so we're going to call that hub drill 6.8, and let's have a look for that file, hub drill 6.8. There's our little bit of code there. Let's just run that. Just slow down the maximum velocity slider to 0 at that point, and just check all your positions and clearances, and you can just gradually ease it out. That seems okay. Now we can go full on. So that's quite a slow way to do it with all of that retraction, but you know, as I always say, if you can run it automatically, you can go away and do something else, and it doesn't matter whether the part takes 2 minutes or 5 minutes. It's automatic production that's what matters. And then we've got the little 12mm 12.1 bore in the end. So we're going to use a boring tool. We could use a counter bore tool, but the advantage of a boring tool is you can use that tool for chamfering the edge and other jobs, so it's worth setting it up because it's versatile. Let's have a look at the conversational. So be very careful when you're doing small diameter boring that your back off doesn't crash into the work. So you take your first cut and then you back off, and the back of the tool could hit on the bore. So you might have to set a fairly decent cut if your boring bar is quite a big size relative to the hole. On the other hand, you could put a very small boring bar in and you won't have the stiffness, and you'll have tool flex and all sorts of errors and issues there. So it's a wee bit tricky doing small boring work like this, so be a bit careful with your tool clearances and so on. Let's just run that now. So we're calling that hub 12.1 bore file. Where are we? Hub 12.1 bore. Is it there? It looks okay. Slow down the maximum velocity slider again. It'll do a tool change in the turret. Just pause there, have a look, tools there, look at your diameters, have a wee think about it. Looks okay. Bar is good because you can also do the internal chamfer. So there, I put it in at 30 degrees so I can use it, and the cylindrical grinder as a center if I decide to do that. Just pause it and have a wee look and think, okay, looks about right. So there's the little chamfer. It looks great. That small boring bar there is a little CCGT. Been having quite a bit of success with it. It's just a cheap Chinese one. CCGT 6mm. I'm using aluminium tips because they look like they're diamond ground. They're razor sharp and they hold up quite well on small boring bars, machining tool steel and medium tensile steel. They're working out really well. If you use a pressed tip like that one that's in that bar, they probably last longer because they're stronger. The edge is a little bit duller. They're sort of formed to that shape, and they're good for roughing in the bigger sizes, but you can't really do precision finish machining in steel because they're just not sharp enough, and I prefer the aluminium type of tip, which is much sharper. Well, I had a backup plan if that didn't work out. I was going to use this tool that I ground out of a blunt 8mm carbide milling cutter, which would be even better. Stefan Goswinter has done a really good video on grinding your own boring bars on a D-bit grinder, and I've chosen to grind the other end, the flute end, because it gives a kind of a swath retraction groove in there. and you can optimize the end shank to tip diameter as long as you don't mind using a bigger end mill in the first place. That's an 8mm shank, and it comes down to a much smaller bore. So that would have been even better because you can diamond lap it to be really sharp. But the little carbide insert seems to have worked well enough, so I've just stayed with that. And the other advantage of grinding your boring bar from the flute end of an old blunt cutter is that you can have better top rake. See the top rake there? You can get a better rake that way because it's part of the milling cutter rake to some extent. So I think that's a good option if you've got old blunt milling cutters, is to grind them into precision boring bars. You can make them extremely sharp and stiff because they're solid carbide and they cut really well for finished machining. And I think that's just about ready to flip around it and do the next one now. So what I'll do is combine all of those little bits of code into one combined automatic run all, machine hub all, machine all the ends of the stock to those dimensions, and then I can flip them round in the chuck, and using the same code but adding a parting toolpath, I can machine the other ends and then part them all off. So okay, we've run all of the individual little bits of code that we've conversationally created. Now we can put them all together into a combined. So we just insert each of the files, look for the file, choose it, and insert it at the end of, so we can, the end of the list of little bits of code. We can reposition the order by moving up and moving down. So when we've got them all in place in the order we want them in, then we can save them. I've already done that, so let's just have a look at them now. So we've now got them all saved. We're going to call this Hub All 2. And we can have a look at the graphics. How it's really worth having a procedure here. When you tested all the little individual bits of code, as I mentioned earlier, if you found an issue with one of them and you had to hand edit it, make yourself a little note as to what you did. You know, if you've got a memory like me, it's really worth writing things down. There was 2 bits of hand editing I had to do. And now when you've combined them all, it may have reverted back to how it was, to its default settings by being processed through the conversational. And I can see the issue has reappeared again. See this little dotted line? It's a retraction from the radius, and it crashes into that diameter. It should have backed off to there and then come down, but for some reason it's come down to there. So I need to go in and add a Z move in there at that point. And there's another little issue, OD face redo. So when I'm coming in with the finishing cut, the tool's set up with this version of the software to plunge in the full depth there, and that's not suitable for this geometry of tool. I need to come into the roughing depth, come up, go full depth and face that way. So there's a little bit of editing there to do, and then I'll have it back to how I've refined it in the individual little tool paths. Well, let's just go through editing one of them. This could be useful for some of you. So you find the area where there's the issue. Here we are, a finish pass on that face. Let's see, it's going to the 20 diameter and 30 deep, whereas it had roughed to 29.8. Well, that's not a good idea. And then it backs off, comes back round to the 52 diameter, 30 deep, and takes a pass through down to 20 millimeters. Well, that part of it's fine. So we just need to change this one here to 29.8 and delete that out. So now we're going down to that depth, coming back round, coming down, and maybe we'll put in here, instead of going down to 20, we'll go down to 19.9 to give us a little bit of an undercut there. and then maybe we'll go enter. So we're going to go G1X 20.2 for example. So we've just done a little plunge undercut there, gone back out to 20.2, then we're going to zip away at an angle GO to 52 Z1. So that's okay now. We've fixed that little error. We then look for our other little bit of code error, and it's another retraction we've got to change, and then we can run it with those solutions in place in the combined code. Let's just run that other little issue. So we just scroll through until we find end of corner radius, because that's a bit of code just before the issue is. Now for some reason it didn't retract out far enough. It's only retracted to Z minus 29. So we're going to put in retract to Z1. And now when we come to the next little bit here, instead of it crashing in to that diameter at 19.7 into the 20 mil diameter, it'll be at Z1. So that should be okay. Now we can save that, and we should have everything fixed. It looks okay. So when you run the first combined bit of code, still be a bit careful and watch closely, particularly at those 2 points. Slow it down. You know, there's quite a bit of work in this, isn't there? I mean, setting all the tools in the first place and then fine-tuning your code is quite time consuming, and it's definitely worth it if you're going to make 3 or 4 parts or 30 or 40 parts. But if you're only going to make one, I think I'd use the manual lathe every time. Well, that looks good. So the big advantage of CNC, I'm always going on about this, is that it's really good for production. And if I want to make these again in a couple of years time, I can use the same bit of code. So it's really important to save it, you know, put in a USB key, open up grinding wheel hubs, hub all 2, copy to USB. I'm just going through this to really reinforce the important. Now we've got that in our USB and we can eject it. In here is the part. It's fantastic. So on your drawing, it's a really good idea to write down some key information, because it might be in a couple of years time you want to run these again. You might decide to manufacture these as a product, you know, grinding wheel hubs. So write down the key things, you know, your 1045 steel, and your speed is 100, and your depth of cut is 0.2 for chip breaking, and your tool numbers. Tool 2 is the Iskar trigon, tool 3 is the threading insert, tool 5 is the spot, tool 9 is the 6.8 drill, tool 1 is the 7mm insert boring tool. Now that is enough reminder with this, and with the USB key you can set the job up again and run it really easily and safely. And this is the beauty of CNC lathe machining. Alright, thanks for watching part 2, guys. The last part, part 3, will be coming up shortly. This whole series of projects I find really fascinating. You can probably tell I do it more for the love of it than anything else. So stay tuned for the next part. Cheers.